Alright, the next thing we're going to talk about is something called electronegativity. Okay, now remember we said that ionic compounds are held together by the attraction between the positive ion and the negative ion's electrostatic attraction. Well, covalent compounds are held together kind of a different way, but it's still the same thing. Okay? In a covalent compound, since the atoms are now overlapping orbitals instead of just giving and taking electrons, their nuclei, they get very, very close together, and the nucleus has all that positive charge, and the nucleus has a pull on anything negative close to it. So electronegativity is defined as the ability of a nucleus to attract the electrons of another atom. Okay. And so it's simply something we kind of measure. Okay. And let me show you kind of in general. So you should have your electronegativity table. If you don't have it, go ahead and pause and then go ahead and get it out. Okay. Now, I don't have an electronegativity table in here, but I have a blank periodic table. So what we're going to do is look at just generally where the values for electronegativity fall on the electronegativity table. Now, we're going to call this our EN table. EN for electronegativity. Now, if you look at your electronegativity table, you'll notice there's a lot of numbers. It looks just like a regular periodic table, except there's a little number underneath each of the symbols. It goes from 0 to 4. I think yours actually is 3.9. And if you look for the highest number is way over here. This is fluorine. It's electronegativity around 3.9 or 4.0. Way down here in the left corner, we get francium, which is about 0.7. Pretty wimpy. Okay. And if you look, that there's no electronegativity values for this family, the noble gases. Why? Okay. Because they don't bond with any other atom, so their nuclei don't really have any attraction for any other atom's electrons at all. So we don't give them electronegativity values. So in general, we can say that the values, if you look at them, as you go from left to right, the numbers get bigger, and as you go from the bottom to the top, they get bigger. Okay? So that's why the big numbers here and little numbers down here in the corner. So this is called the electronegativity table. Okay, so what we need to do, so what does that tell us? Well, that's kind of interesting, but what does the electronegativity table actually do for us? Well, the electronegativity table, if we compare the difference in electronegativity values for two atoms, this is going to tell us what kind of bond will they make. Okay. Because we've been talking about ionic and covalent bonds, and we said the ionic bonds are between metals and nonmetals, and covalent bonds are between two different nonmetals. Well, what about the metalloids? Okay, because they're sort of metallish and sort of non-metallish, so how do we know what kind of bond they're going to make with something else? Okay, and the other thing that they're going to tell us is the electrons and what we call electron distribution in the bond. We'll talk about what that means. Okay, so we're going to make a little line, if you will, here. You should make a copy of this in your notes. This is going to show us when we're going to do the difference. Now, difference means what? Difference means we're going to have to subtract the values. Okay, so the difference could be nothing, And the differences usually tends to go to around 2.5 is about the largest difference between two atoms that we find. Okay. 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 It's going to be a little bigger. Okay, if the difference is pretty small, okay, either there's no difference at all or the difference is as little as 0.4, this is going to be a covalent bond, which means they're going to share, which means they have fairly equal pull on the electrons of the other. That sounds kind of like an electron, a covalent bond where they're sharing. Okay. If we go up to about 1.7, this is also a covalent bond. Well, then what's different about these two? Well, these, they have fairly equal pull, so they're sharing equally. Equal sharing of the pair. Okay. If we think back to our French fry analogy, you and your friend buy the French fries together, and you sit and you eat one fry for every one fry that your friend eats. So you eat pretty much exactly the same amount of fries. You split the fries equally between you. Okay. However, maybe one of you you help buy the fries, but one of you is really hungry or really likes French fries, and so you eat more French fries than your friend does. Well, then you're not sharing very equally. Now you're still sharing because you both get some fries, but it's not very equal anymore. So we call this one non-polar, and this is called polar. Okay, and we'll come back to what do those terms actually mean. Why do we call equal sharing non-polar and non-equal sharing polar? What does that mean? We'll come back to that in just a minute. But let's talk about this. Well, what about this if there's a big difference? Okay, 1.7, more than 1.7, up 2.5 or even bigger. So in other words, one of the nuclei has a huge pull and the other nuclei is pretty wimpy. This means there's no sharing. Okay, no sharing. One of the nuclei is just going to pull the electrons right off the other. Well, what's that? That is an ionic bond. Well, let's talk about what does it mean if we're going to say, okay, polar or non-polar. Polar. Okay. Okay, if they're not equally sharing, that means that the electrons are going to be closer to one atom. Okay, so for example, hydrogen and chlorine are sharing. This is going to represent the pair of electrons. I didn't draw the extra lone pairs on chlorine. Okay, hydrogen and chlorine are pretty close to electronegativity, but their values are just farther apart. Okay, it turns out that the chlorine has more pull on the electrons than the hydrogens do, which means that the electrons are closer to this end, okay? Which means that hydrogen sort of gets kind of positive-ish because the electrons it's sharing are pulled over here. Okay, so it's kind of like this, the end of the bond, if you will, is kind of negative, and this end of the bond is kind of positive. Well, does this mean they're ions? No, they're not ions. So we don't use positive and negative symbols alone. We use these funny looking little things. It's called, this is a lowercase d in Greek. This is a delta. Okay. Okay, so these are called partial charge notations. Okay, so this means that this end is sort of negative and this end is sort of positive. So this is what we mean by a polar bond. Well, if you look at the two electronegativity values, chlorine's electronegativity value is larger than hydrogen, so it will be the negative end of the bond. Okay. So what does nonpolar mean? Nonpolar means that the electrons are pretty much equally shared. The middle, so there's no negative or positive end to the bond. So that's what I mean by poles. Okay, polar, okay, just like there's a north and a south pole, there's a positive pole and a negative pole. Nonpolar, there's no negative or positive end. Okay, so this is like if chlorine and fluorine were bonded. their electronegativity values are so close that they're pretty much sharing this electrons perfectly equal. There's no negative or positive end. So this is called a nonpolar bond. Okay, and the last section we're going to talk about is polarity of molecules. Well, what does that mean? Well, we just talked about just two atoms and the fact that you can have a negative end in that bond and a positive end in the other bond. But if we look at the whole molecule, a large molecule, okay, let's look at, remember our old friend pH3? Okay. We want to talk about how are the electrons distributed in the whole molecule. Well, if you look at the pH bond, the pH bond is actually, it's a polar bond. It's pretty close to being nonpolar. It's not a huge difference between the P and the H. But if you look over here, there's this electron pair over here on the phosphorus, which means that even though that there's other electrons here that are being shared relatively evenly, there's this whole region with these unshared pair of electrons. That means that this molecule actually has a negative, partially negative end, and this other, anywhere else would be considered partially positive because there's more electrons over here. So this is called a polar molecule. Even though the bonds in the molecule are more nonpolar than they are polar, the presence of this lone pair, as we call this non-bonding pair of electrons, makes the whole molecule have kind of a negative or positive end. So that's the first thing you need to look for. If you're looking at a molecule, you have to draw the Lewis dot structure. The first thing you look for is you ask yourself, is there lone pairs on the central atom? That will make the molecule polar. Now, it doesn't mean there's lone pairs out here on the non-central atom. Those will have nothing to do with whether the molecule is polar or not. The second way you can tell that a molecule is not going to be polar, if there aren't any lone pairs, is the molecule is non-symmetrical. Okay. So if you look at, let's look at carbon dioxide. Remember carbon dioxide? We've done that before. So okay. Now if you look at this molecule, now I didn't draw it perfectly, but this molecule, if you look at it, it's got a left side and a right side that are perfectly identical. Now the carbon to oxygen bond is actually a polar bond. Okay? Whether it's a double bond doesn't make any difference. So that means that yeah, the electrons are pulled over here, and yeah, the electrons are pulled over here. But because the electrons are pulling perfectly in opposite directions, they cancel out. So this is a nonpolar molecule because it is symmetrical. Okay, so when you are looking at these, you will need to look for two things. You need to look for the central atom having lone pairs. That means yes, it's polar. Or if it's not a symmetrical molecule, that also means yes, it's polar. Okay, so polar molecules have a lone pair or they are not symmetrical. Now be really careful. I'm going to do one more example for you that tends to be kind of tricky. That's H2O. Alright, so in this case we got O. Okay, and students tend to say, oh look, it's a symmetrical molecule. You got to check number 1 before you check number 2. So you look and say, oh wait, there are lone pairs on the central atom. Yeah, it looks symmetrical, but the lone pairs on the central atom will make it a polar molecule. Okay? So this end of the molecule is the negative end, and this end of the molecule is the positive end. So before you get all excited about the symmetry, check to see if there's lone pairs on the central atom first. If there aren't, then ask yourself, is the molecule symmetrical? Does the left side look at the right side? Or if there's 3 parts, are all 3 parts identical? If there's 4 parts, are all 4 parts identical? If they're not, then you can say it's a polar molecule.